Good evening, everyone. We're from Group 6, Computational Thinking 5, and today we're going to present to you our case study about warehouse inventory management. And the example that we're taking is the warehouse inventory management of food and beverage business. So to start, my name is Rizqi Naufal, and our group member consists of Alisha, Zafira Nugrahaningsih, Elangga Mudhofar, uh, me, myself, Rizqi Naufal, Mechra, Habiel, Azzikra, Monika, Dewi, Angelina, and also Nadine, Anindya, Putri. So without further ado, let's start our presentation.
My name is Mechra Azzikra. So the problem definition of this case is a large warehouse struggles to manage its inventory efficiently, leading to overstocking, stockouts, and increased operational costs. The warehouse want to optimize inventory levels and streamline the restocking process. A study conducted by Georgia Institute of Technology shows that around 70% of warehouse space is inefficient. This inefficiency can lead to a variety of problems such as overstocking, poor safety management, and etc. So the problem statement for this case is design a computational solution to optimize inventory management. The solution should consider historical sales data and demand patterns, storage capacity and shelf life of products, supplier lead times and restocking costs, seasonal demand fluctuation. So we need to create a system that dynamically adjusts inventory placement and robot routing based on real-time order data while balancing delivery speed, storage efficiency, and operational costs. The solution has to incorporate at least one classic algorithm, such as linear search, finding extreme values, greedy algorithm, or brute force.
Okay, now we're moving to pattern recognition. Pattern recognition, it involves identifying recurring trends, behavior, and inefficiencies within the warehouse system. This helps in predicting future demands, optimizing space, and reducing operational delays. Below are some key patterns that we observe. Next. Okay, the first pattern is demand-based patterns. So high demand products require frequent stock stocking, leading to potential stock out if not managed properly. And if it goes low, demand products remain in storage for longer periods, occupying valuable space and increasing storage costs. And seasonal products experience fluctuating demand, requiring predictive adjustments. And the next pattern is storage and space utilization patterns. Now, frequently ordered products should be placed near dispatch areas to reduce retrieval time. And perishable items with shorter shelf life should be strategically to minimize waste. And overstock items should be flagged to avoid unnecessary holding costs. Okay, moving to the supplier and lead time patterns. So the product with longer lead times require early reordering to avoid stock out, and suppliers with inconsistent delivery times increase uncertainty, necessitating a buffer stock management. And restocking schedule should align with demand forecast to optimize storage efficiency. For the last pattern is robot routing and efficiency patterns. Now, these routes with high traffic slow down order fulfillment and should be optimized. And shortest path for robot movement should be identified to improve delivery speed. And last one is orders containing multiple items should be grouped efficiently to minimize robot travel distance.
Okay, my name is Elangga Mudhofar, and I'm going to tell you the data representation and abstraction. So here's our data table that we made by ourselves. So it has the product ID, items, demand rate, stock level, lead time, shelf life, and storage zone. So the stock level is our current inventory, and the demand rate is the daily product consumption. Lead time is days required to restock. Shelf life as the maximum storage duration before expiration. Storage zone as physical location in the warehouse. So we divided our product in a storage zone based on their characteristic. So, for example, in the product ID of 6D, the frozen food, we place it differently from another items in storage zone D. Next. Okay, now for the abstraction of the robot travel time. So, robot travel time is time taken for a robot to retrieve and place the product. So here's our warehouse floor plan. So we made this as efficient as it could be. So the robot will retrieve and place product approximately 1 to 5 minutes. Next.
Okay, hello everyone. My name is Alisha Zafira Nugrahaningsih. Here I will present the data representation of the operational cost. So after we find the data representation that includes the item, stock level, lost sale quantities, and also unit price that I obtained from the market price on the internet, I can calculate the total operational cost by calculating the total of order cost, shipping cost, labor cost, automation cost, restock cost, storage cost, holding cost, and also processing cost. Next. So to solve the problem, we chose two algorithms. First is greedy algorithm, where it ensures a balance between storage and cost efficiency with minimal computation. And we also chose the brute force algorithm that ensures the best solution by evaluating all possible storage and cost combination and selecting the most optimal one after exhaustive computation. Next.
So hello again, my name is Mechra Azzikra. I'm going to explain to you the flow chart. So we start by collecting key data like sales trends, storage constraints, supplier lead times, and seasonal fluctuation. Then we analyze this data to identify trends, determine reorder points, and predict demand shifts. Next, we apply method like linear search, greedy algorithms, or brute force to find the best inventory strategy. If inventory level doesn't meet the requirements, we adjust dynamically by optimizing storage and prioritizing fast-moving items. We also track stock movements and in real time to detect issues like overstocking or stock shortage. Finally, we refine prediction and improve efficiency by learning from data, ensuring the system evolves over time.
Hello everyone, my name is Monika Dewi Angelina, and now I'm going to explain briefly the pseudocode. First, the system starts by analyzing demand, assigning a score to each product based on its historical sales, seasonal trends, and shelf life. It then checks storage capacity to make sure that adding new stock won't overcrowd the available space. After that, using a greedy restocking strategy, the system prioritizes products that have both high demand and short lead times. It further boosts efficiency by relocating high demand items closer to the picking zones. For robot routing, a nearest neighbor approach is used to cut down the travel distance during item picking. Finally, the system continuously updates inventory reports and route plans in real life to stay adaptable.
Okay, hello everyone. I'm Muhammad Rizqi Naufal. So next we have brute force for optimal stock levels and brute force for inventory placement. So firstly, for optimal stock level, this function determines the best stock level by evaluating different options and selecting the one with lowest cost. And then the way it works is firstly we have to initialize the best stock level and as a starting point, and then set the minimum cost to infinity to find the lowest cost. And then we look through all possible stock level, and then simulate its stock usage and replenishment, and then calculate the cost of maintaining the stock, including storage and stock out costs. Uh, and then if the current cost of maintaining the stock is lower than minimum cost, update minimum cost and store the best stock level, and finally return the optimal stock level. For the inventory placement, first we have to initialize best placement and set minimum retrieval time to infinity, and then loop through all possible ways of placing the items in storage zones. And then third one is simulate retrieval times, and then calculate the total retrieval time. If the calculated time is lower than the minimum retrieval time, we update the minimum retrieval time and store the best arrangement, and finally return to the best arrangement. And then for brute force for demand peaks and also brute force for robot path optimization. For the demand peaks, firstly we initialize max demand as 0 and then peak period as none. And then loop through each period in sales data, compare current sales with max demand. If sales is higher, update the max demand and peak period. And then finally return the time period with the highest sales. Next for the robot path, we initialize the best route as none and minimum distance as infinity. Loop through all possible paths between start node and end node, and then calculate the total distance for each path and compare with minimum distance. If it's shorter, update minimum distance and start the path as the best route. And finally, return the best route with the shortest distance. Next, we have the greedy algorithm for optimal stock level. Firstly, we have to initialize stock level and total cost as 0. Loop until storage limit is reached. Select the item with highest demand. Check if adding it exceeds maximum storage. If not, add it to stock and update cost. If yes, stop the process. And third one, return the final stock level and cost. Sorry. And then we have the greedy algorithm for inventory placement. Uh, is to find the best way to place inventory item in storage room. First is sort item by shelf life, and then for each item, find the closest available storage zone, assign the item to that zone, and repeat until all items are placed, and then return the placement configuration. Next is gradient algorithm for deep peak demands. Use the built-in max function to identify time period within the highest demand, and then the function use sales data as a key to compare demand values. It returns the time period with the highest demand. Sorry. And then for the greedy algorithm for robot path optimization, start at start node and moves greedily towards the closest neighbor, and then repeats the process until it reaches the end node, returns to the final route taken.
The conclusion from our presentation are, in the study, we developed a dynamic inventory placement and a robot routing system using a brute force approach. The goal was to balance delivery speed, storage efficiency, and operational cost while dynamically adjusting inventory locations based on real-life order data. Next, by decomposing the problem, we identified key challenges, which are optimizing storage location, ensuring efficient robot movement, and adapting to real-time inventory changes. Through pattern recognition, we discovered that frequently ordered items should be placed closer to the dispatch area, and orders with similar items should be grouped together. Using data abstraction, we represented the warehouse as a grid with items stored in specific cells and robots moving in 4 directions. We then implemented a brute force approach, which explored all possible inventory arrangements and robot routes, selecting the one that minimized retrieval time.
And finally, that concludes our presentation from Group 6. Thank you for listening and watching, and see you on next occasion.